Okay, so I'd like to start with reviewing some basic facts from life of Aharonov-Bohm interferometers. As you know, as you probably know, the symmetry of transport coefficients of a mesoscopic device in respect to change of the sign of the magnetic field is governed by Onsager-Buttiker relations, which in case of a two-terminal device take a particularly simple form, which is shown here, that the linear response conductance of such a device is an even function of magnetic flux. In particular, if we talk about an Aharonov-Bohm interferometer, magnetic field can very frequently be replaced by magnetic flux, and then we can reformulate this property by expanding Aharonov-Bohm conductance in harmonics of magnetic flux, and stating that the phases, additional phases in all the harmonics should take values 0 or pi. And this is why this property is often referred to as phase symmetry or phase rigidity or phase lock-in. So naturally, if we have some kind of symmetry, we're interested in how to break it. And there are, I think, 3 generic ways of breaking this kind of symmetry in respect to magnetic field. Here you see one very popular way, which originated in connection to attempts to measure transmission phase of an object placed in one of the arms of the interferometer, which of course cannot be done because of the phase rigidity, which limits the phase to 0 pi. So you can use open interferometer, which is actually a multi-terminal interferometer, which obeys certain set of Onsager-Buttiker symmetries. But when it is looked upon as a two-terminal interferometer, the phase symmetry is broken because number of particles which enter interferometer through the left lead is not necessarily the same as the number of particles which leave it through the right lead. Now, another way to break the phase rigidity is by going beyond the linear regime, where Onsager-Buttiker relations, of course, don't work because they apply to linear response case. And there is a lot of work done. Again, there are a lot of experimental and theoretical work done in this direction. In particular, there is a landmark theoretical paper by Sanchez and Buttiker, who studied first nonlinear corrections to current and showed that already first nonlinear correction to current is not necessarily symmetric in magnetic field. And they made a general statement that asymmetry appears to the extent that the potential within the device is not an even function of the magnetic field. And I'd like to use this opportunity to advertise our recent contribution to this subject, which we did in collaboration with a group of clowns Senslin from Zurich. And we studied somewhat opposite limit. We studied high bias regime and interferometer with discrete levels in regime of Coulomb blockade. And we also made some general statements that any deviations from phase rigidity appear only after the onset of inelastic cotannon, and you can see strong asymmetry only in very special circumstances. So now I'd like to move on to what my talk is about the third way of breaking the phase symmetry by coupling an interferometer to an environment. There is a very recent work cited here by Sanchez and Kang, who showed that this happens only if the environment which interacts with the interferometer is a non-equilibrium one. If the environment is an equilibrium, you can use certain kind of time reversal symmetry arguments to show that phase rigidity would hold. So before moving on to my project, I'd like to remind you what is a wedge path interferometer. Wedge path interferometer is a device where one of the arms of the interferometer interacts with a certain kind of detector. For example, here you see a quantum dot in one of the arms of the interferometer, which coupled via Coulomb interaction with a quantum point contact. So if electron chooses to go through the quantum dot, then conductance of the quantum point contact changes, and you can detect that electron went through this arm of the interferometer and not through the other one. And in connection to this particular figure was stolen by me from the paper by him and Kang, who pointed out that in such a closed interferometer, because interaction with the quantum point contact, Aharonov-Bohm oscillations can lose their symmetry in respect to magnetic field. And I'm going to build up on this idea. I suggest to consider an interferometer like this, which is a closed Aharonov-Bohm interferometer. There is a quantum dot in each of the arms. And one of the quantum dots is coupled to a quantum point contact via Coulomb interaction or by some other means. But for simplicity, we suppose that it's Coulomb interaction. So first of all, I suggest to look at this slightly different, not as a wedge path interferometer, but as an interferometer coupled to an environment. Quantum point contact is an environment, and we know that it can be easily driven out of equilibrium by applying finite bias to it, right? So this kind of system is in fact an ideal system for testing the predictions of Sanchez and Kang regarding breaking of the phase symmetry by coupling to an environment. Further, I'd like to stress the importance of this quantum dot in the reference arm of the interferometer. We can use a phenomenon of so-called phase jump to actually enhance our ability to observe breaking of the phase symmetry, and I'm going to say more about this in the next two slides. Then, after all this is said and done, we can, I will show that we can do practical application of this setup by extracting the transmission phase through the quantum dot in the reference arm. In this sense, this setup can replace the traditional experiments with open interferometers. And finally, there is an interesting photon-assisted current which flows between the interferometer leads even when the bias between left lead and right lead is 0, right? So this is the summary of what I'm going to talk about. First of all, phase jump. I'd like to remind you what it is. It is a phenomenon which occurs in Aharonov-Bohm interferometers which contain a quantum dot in their arms. So this is a closed interferometer, so the phase should be either 0 or pi. But it turns out that it is different depending on whether the level in the dot is below the Fermi level of the leads or above the level of the leads. So now if you sweep the level across the Fermi level, the phase at some point has to jump between 0 and pi. And this is well known theoretically, experimentally. Here I show you the results which were obtained by modeling this interferometer using standard Keldysh non-equilibrium Green's function technique. And let us first look at this picture in the upper left corner. For this picture, the bias applied to the quantum point contact was taken to be very low, so you can forget for a minute about quantum point contact and see what happens when we have a phase jump. Along horizontal axis, we have a magnetic field. Along vertical axis, position of the level in the reference arm in respect to the Fermi level. Now you see that when it is below the Fermi level, you have two maxima and one minimum in the range of the magnetic fields chosen. Whereas when it is above the Fermi level, we'll have two minima and one maximum in between. So the phase, the Aharonov-Bohm phase, changed between 0 and pi. Instead of minima of oscillations and 0 magnetic field, we have now maximum. And how it happened? It happened because the amplitude of Aharonov-Bohm oscillations disappears when we sweep the level across the Fermi level. So phase can jump. There is no any physical contradiction in this. Of course, only amplitude of the main harmonic of Aharonov-Bohm oscillations disappear. If you draw mentally a line here, you can see that you have actually 4 maxima, which means that the oscillations are dominated by the second harmonic. Now, if you look at the plot below, the plot below is the same interferometer, but with finite bias applied to the quantum point contact. First of all, there is a trivial effect that there is an energy shift due to interaction, and the point where the phase jump occurs is shifted in energy. Now, I don't know if you can see there is asymmetry here in the vicinity of the phase jump. Right? Can you see it? Okay, so there is asymmetry, which is noticeable near the phase jump, but which is not noticeable far away from it. This happens because the odd harmonic of Aharonov-Bohm oscillations, which is shown here, it is about order of magnitude smaller than the even harmonic of the Aharonov-Bohm oscillations. But when we go in the regime of the phase jump, the even harmonic of Aharonov-Bohm oscillations become very small and becomes comparable to the odd harmonic. And this is why in this regime, any asymmetry should be very manifest. And I also extracted the phase of Aharonov-Bohm oscillations. You can see that as we increase bias, the phase, instead of abruptly jumping between two values, starts to flow smoothly between them. So now a little bit of mathematics. We can define a transmission phase through the quantum dot in the reference arm, as shown here. And then we can extract the real part of this transmission coefficient just by looking at the amplitude of the odd component of the Aharonov-Bohm conductance, which can be extracted from the Aharonov-Bohm data. Right? I suggest that this is a better way than actually tracking the phase of Aharonov-Bohm oscillations themselves. Because the phase of Aharonov-Bohm oscillations, as we know, is not necessarily the transmission phase through the quantum dot. It is true for open interferometers, and it is even more obvious here because the transmission phase through the quantum dot changes on the scale determined by the coupling between this quantum dot and the leads. Whereas the transmission phase through the Aharonov-Bohm interferometer, the phase of Aharonov-Bohm oscillations, is determined by the strength of the coupling between the interferometer and the quantum point contact. So knowing this, knowing the real part of the transmission coefficient, and by measuring separately the amplitude of the transmission coefficient, we can extract the cosine of the transmission phase and restore the phase. Or actually, we don't even need to go through this procedure. We can simply look at the zeros of the real part of the transmission coefficient, which correspond either to the phase taking value pi over 2, or it corresponds to a phase jump if the real part of the transmission coefficient disappears simultaneously with the amplitude of the transmission coefficient. Not necessarily phase jump. It can be phase lapse or other more complicated kinds of the phenomena. So do I have much time left? Oh, okay. So I will not talk in detail about the physical processes responsible for breaking of this phase symmetry. I just would like to point out that, first of all, the mechanism which is responsible for this was studied by Holstein and by Antin Wollman and co-workers in connection to photon-assisted transport, or phonon-assisted transport. And it was also studied by us in connection to co-tunneling. And basically, it has to do with virtual transitions in which intermediate virtual states are on the same energy shell with the initial and the final states. So if, I don't know if it's a satisfactory explanation. But talking about the processes, I'd like to point out one interesting thing, that we may have high-order inelastic processes, right, which which take place even if the bias applied between the interferometer leads is 0. So electron from below the Fermi level in one of the leads can get excited to a high energy state and move into a state above the Fermi level in the other lead. Or it can move from the right lead to the left lead. But if we had only one quantum dot, the processes transferring electrons from right to left and from left to right would cancel each other. However, this system is somewhat equivalent to a 2 quantum dot short noise detector, except that the dots are not in sequential arrangement, but in the 2 arms of the interferometer, and non-zero current flows. This current has interesting properties in respect to the sign of the magnetic field. If first of all, in order to have non-zero current, it's obvious that we need to have some kind of asymmetry between left and right. And this asymmetry comes from 2 sources. It comes from the presence of magnetic field, and it comes from geometrical asymmetry of the device if the dots are not equally strong coupled to the left and the right lead. Now, if we assume for a moment that the device is perfectly symmetric, then at 0 magnetic field, also, we have everything perfectly symmetric and no current flows. Now we apply magnetic field, a current will flow in some direction, let's say from right to left. If we change the sign of the magnetic field, then the current should also have to change the sign. So this current, which flows at 0 bias, is inherently non-symmetric in magnetic field. It is odd. Now, if in addition we have some geometric asymmetries in the device, it can be shown that these asymmetries lead to current even in magnetic field. So overall, current is going to be neither even nor odd, but somehow not symmetric in magnetic field. So I'd like to summarize. We proposed to use wedge path detectors, which can be produced in many labs in order to study breaking of the phase rigidity in controlled way. We showed that exploiting the phenomenon of phase jump can facilitate such a study and make it much easier in the lab. We proposed the way to extract transmission phase through a quantum dot in the reference arm of the interferometer. And finally, there is also photon-assisted current, which has interesting properties in respect to the sign of the magnetic field. Thank you for your attention. Well, first of all, it's a good question. Okay, so there is some coupling just from the geometry of the device, right? But also, it's not actually the coupling which is important, but there is this dephasing rate, lowercase gamma, which was in one of my slides, which depends on the bias applied to the quantum point contact. So as the bias increases, this dephasing rate increases. However, one has to be careful not to increase it too much, because this dephasing rate plays at least two functions. On the one hand, it's responsible for the relative strength of the odd Aharonov-Bohm oscillations. But on the other hand, the same rate is responsible for suppression of the Aharonov-Bohm oscillations as a whole. So, it has to be adjusted carefully.
Okay, just come back. But there are numbers in the experiment how strong the electrostatic coupling is. So the end is concept of proportionality numbers. Which one do you think?
Well, I assume it to be a small coupling, right? In order not to suppress completely Aharonov-Bohm oscillations. But I have to say that in such Aharonov-Bohm interferometers, there is no complete suppression of Aharonov-Bohm oscillations, right? Because in addition to electron just going through the quantum dot and to the other lead, there are also processes when electron goes to quantum dot, walks around the interferometer and goes to the other lead, and it can travel many times. And these are exactly the processes which are responsible for this effect.
Can you also clarify, please, what is exactly the difference between what you consider as conventional way to determine the phase and your way of determining the phase? I mean, in both cases you measure conductance, isn't it?
Right, but the difference is that there are three ways of breaking the phase rigidity, as I showed. And traditional way to break it in order to measure the transmission phase is by using multi-terminal interferometer geometry.
Yeah, that's clear, but you were talking about how to determine the phase itself analytically, and analyzing the data, so to say. So,
yeah,
I mean, you have some expression G equals something, and
yeah,
what is phi. And you said that you have, you recommend to do something different.
Yeah, there are several reasons for doing this. I suggest to take the odd in magnetic field component of Aharonov-Bohm oscillations and extract phase from the behavior of the amplitude of this harmonic.
Of this conventional way.
And conventional way is that it was believed, at least initially, that the phase of Aharonov-Bohm oscillations, the phase shift of Aharonov-Bohm oscillations, is the same as the transmission phase through the quantum dot. But then later it was shown to be not true, right, by Joe Imrie and co-workers.
Can you again, at the end you try to explain intuitively why this breaks the phase. Can you repeat it? Because
Okay, it works. So what happens is that you have to go to high order processes, right? High order, let's say, first of all, first of all, for simplicity, I do a kind of Schrieffer-Wulff transformation. So you cannot study phase jump after you do Schrieffer-Wulff transformation. But in order to understand the physics, no, not Schrieffer-Wulff, but I transform Hamiltonian so that I talk about processes when electron is transferred from left to right. I'm just trying to explain this picture. You see what is shown here. And then, yes, it's third order in these processes. It's in a way, it's like if you do expansion in J for Kondo effect, right? But you see that you have each contribution consists of first order tunneling amplitude and second order tunneling amplitude. And second order tunnel amplitude contains this factor associated with deviation from energy conservation in the intermediate state. And when the intermediate state has the same energy as the initial state, then this imaginary part of the denominator gives you additional phase shift. This is how it can be understood mathematically.
No more intuitive explanation.
Well, I can't really say.
Going a little bit beyond time. I mean, if it's short questions, then okay.
Why did you say that you're coupling to a non-equilibrium situation? Suppose you've got coupling to phonons at
No,
zero temperature. Is the phonon bottleneck or what?
No. At Anzager-Butiker relations, which I mentioned in the beginning, can be proved on the basis of purely time reversal symmetry arguments. Right? So for any system which is close to equilibrium, you can prove that linear response properties satisfy these relations. Now, it doesn't depend on whether you have interaction or no interaction, because it's a very general symmetry argument. And Sanchez and Butiker show that in non-equilibrium situation, it's not so.